There are two main life cycles for any star, all right? Completely dependent on how it, or the size of the star when it's born. So how does it start will determine which cycle it takes, which path it takes throughout its whole life. The two cycles are either for a small star, which our sun is. It's a very small star, in fact. It's just that it's so close, that it's so bright. So any small star or star that has a very similar mass, and again, the two cycles that it can take throughout its life completely depend on the mass of the star if you want when it's born. And if it's a small star, which our sun is, then it will take the first life cycle. So the first life cycle that we have for small stars and stars like our sun start off as a nebula. I'll go through what happens at each stage and what's really going on, but just for now, the cycle itself starts off as a nebula, which is essentially just a cloud of gas and any dust. That nebula will come together and it will form what's called a protostar, which is the first stages in which the star will switch on, so it will begin to emit light, but it hasn't technically become a real star. So no fusion has happened yet as a protostar. Then the fusion reactions, the nuclear fusion inside the star begin to happen. It becomes a main sequence star. Then it will become a red giant. So this is the life cycle that our sun will take. After the main sequence, which is basically the bulk of its life, so the majority of its life is almost like being during adulthood. So being a baby lasts a very short time, being a child lasts only a short time, but being an adult will last the longest, all right? So this is the main sequence period. Then it will become a red giant. During this stage is when our sun is going to get so big that it swallows Mercury, Venus, even the Earth, all right? We've got a few billion years before that happens. Then what happens is it leaves out what's called a shell of gas, technically called a planetary nebula. In the GCSE, they only really require a shell of gas, but if you want to use the term planetary nebula, then that would be even better. And what will be left in the middle of that shell of gas for our star is a white dwarf, all right? That's the life cycle that we're on. It's the life cycle that any star that has a very similar mass, which is technically a small mass, will follow. Nebula, protostar, main sequence. Currently our sun is on this main sequence. It's halfway through its life. Eventually it will become a red giant. It will get rid of its outer layer as a shell of gas, and what will be left is the white dwarf in the center. Nowhere in our life cycle will there be an explosion. Our sun will never explode. What will happen is, yes, it will give off a shell of gas and it will let go of its outer layers, but it will not explode, and it will become a white dwarf. There's no chance of our sun becoming a black hole, all right? And it's because of the mass that it was born with. So when we started as a nebula, we collected a certain amount of mass, which made us a protostar and then a main sequence. And then when we went on to the main sequence, we only had a specific mass, which is not enough for the end to cause an explosion, all right? However, if you are a much bigger star, so a star that has a much larger mass than our sun, all right, we're talking over 5 times bigger, maybe even 10 times bigger than our sun in terms of its mass when it's born, still starts off at the same place. So we both start off as a nebula, we both start off as a cloud of gas and dust, but it just depends on how much dust and gas you have to bring together, or how much you do bring together before you switch on. So you'll bring the nebula together, the gas and the dust, and I'll explain how and why. That then again, exactly the same, becomes a protostar, which is where it switches on, so it does begin to shine, but not because of fusion. Then because it's so massive when it was bringing all that gas and dust together, it becomes what we call a massive main sequence. Same again, the main sequence stage is when the fusion is happening, but for a much bigger star, that main sequence is going to be much shorter. So our sun is currently spending almost its entire life on the main sequence. It will slowly plod along. Fusion will happen for billions and billions of years, and we will basically manage to survive like that for almost our entire life. However, a massive main sequence star spends shorter time on the main sequence, and therefore it won't live as long. It will become a red supergiant, which is just an even bigger version of the red giant. And then at the end of the red supergiant stage will be the explosion, the supernova explosion, which is the biggest event, the most energetic event in that entire universe. And a supernova, the death of one star, this is essentially the star at the end of its life when it dies. Alright? If it dies and undergoes supernova, it can be so bright that it outshines an entire galaxy. If you were lucky enough to be in the line of the supernova, it can basically make the sky bright for days. So it literally outshine the sun, for example. It can make the sky seem as if it's midday from early hours in the morning throughout the whole day. Alright, that's how big an event it is. So after the supernova, you have two options. The star will either become what's called a neutron star or a pulsar. Again, for the GCSE, you only really need to know neutron star, which is a star made primarily of neutrons, not only, but the majority of it is neutrons. It's a very, very small star. For example, at the minute you could fit 1.3 million Earths inside the sun, but a neutron star you could fit into Dubai, for example. It's only around 10-20 kilometers across. However, there is so little space between all the neutrons that make it. It's so dense that it is heavier than any of the planets, the sun, all combined. Alright, so it is tiny, but it is incredibly dense. Alright, that's the neutron star. And then option number two, as we know, it could be a black hole. Alright, even more massive. The bigger the star when it's born, the more likely it will eventually become a black hole. And again, it's something that we've only just seen in photographs, but we can't actually directly observe it. We just know it's one of the most massive things that we have in our universe. It will make entire galaxies orbit around it, or other stars, etc. as well. Okay? So, both cycles start at the nebula stage, both move on to the protostar. A smaller star will become main sequence to red giant, to shell of gas, to white dwarf. No explosion. Or a bigger star, which is not our sun, nebula protostar, massive main sequence, red supergiant, supernova explosion, then either a neutron star or a black hole. Okay? Now, going through what is happening at every single stage. Basically, it all depends on the amount of gravity that is bringing everything together, and then how much force and energy you can provide outwards as well. So starting at the nebula stage for both, all you have is a cloud of gas and dust that is unevenly distributed, so something pulls the other thing close towards it. Gravity basically makes it collapse. So all the gravity of all the gas and the dust in the nebula will pull each other together. Eventually it brings in enough matter. The gravity is basically, the more you bring in, the stronger the gravity will become anyway. So the more matter that is brought together by the nebula, at this stage only gravity is acting on anything. So it's all inwards. The more and more comes, it gets bigger and more massive, even more will come. Eventually, what you have when you move from nebula to protostar is you've brought so much mass, the gravity has brought so much mass together that the pressure and the temperature increases so much that it will begin to emit radiation. Alright? The pressure will get so high that the temperature will rise, and we know if temperature increases, then the wavelength of the radiation that it emits will decrease. So the higher the temperature of an object, the shorter the wavelength. Chapter 5. Okay? So, eventually it will be emitting infrared radiation. The pressure will be high enough that the temperature is hot and heat will be emitted. What happens then is the temperature, the pressure just keeps going, it gets bigger and bigger. The temperature will get high enough that the wavelength of radiation will be short enough that it's in the visible light. So it will shine, you will see some light. However, it's only shining because the temperature is high enough. Okay? At the end of the protostar, the pressure has become so high that the temperature has reached that 10 million degrees Celsius, where you need a proton and a proton to come together under the nuclear fusion reaction and produce helium. And remember, if you have a nuclear fusion reaction where one proton and a proton is put together, you will create energy as well in that reaction. Then you'll take the helium that was created, you'll put it together with another proton, and then more and more energy. So throughout, as soon as fusion happens here, at the end of the protostar, its pressure is so high, its temperature is high enough, basically the star is born and it switches on. As soon as fusion begins to happen, it becomes a main sequence star. Now, depending on its size at the end of the protostar, it's either just a main sequence or it's a massive main sequence. So the nuclear fusion inside a star is what determines the birth of the star. This is what puts it on the main sequence. But this energy, if the fusion didn't happen and the energy wasn't created, then the gravity would just keep pulling and pulling and it would collapse on itself. Alright? The fusion inside the star is what is literally keeping the star alive. So, on a diagram of forces on the star, gravity is always towards the center. Gravity will always act inwards, it will always pull. When fusion happens in the center or the core of the star, we know that energy is produced. That energy that's produced creates a pressure that acts outwards. So you have gravity pulling in, and then pressure from the inside and the fusion reaction happening, pushing out. That pressure that's created balances the gravity, and you have a star which is what we call in hydrostatic equilibrium. Okay? The inwards forces are balanced by the outwards forces, and the star can maintain this balance of forces throughout the whole main sequence. So the only way that a star can survive is because fusion is happening. It is the fuel of the star. Without the fusion, it will not survive. Alright? Something will happen which does happen. Okay? So on the main sequence, whether it's a normal or massive main sequence, fusion reactions of hydrogen nuclei are occurring, energy is being produced, and it's balancing that inward force from gravity. So pressure out equals gravity in. Now, the difference between the two, this one is going to run out of its hydrogen faster. We're okay, we're on the main sequence for billions of years because there is enough hydrogen inside the sun that we can sustain that fuel process and the outward pressure for a long, long time. So we'll be fine. But the massive main sequence, although it's bigger and it has more hydrogen, it's so big that the force that it needs to give back has to be bigger. If you want to have a bigger force pushing out because you have a higher gravity, then to get that bigger force out, you're going to have to burn through more fuel faster. Alright? It's like having a car that has a bigger engine. Although you can fill it up potentially more, it's going to burn through the fuel a lot faster to keep that large engine running. Okay? So a massive main sequence star, it has a larger gravity trying to crush it. It needs to provide a bigger pressure to balance it. If you want a higher pressure out, you have to burn through your hydrogen faster. Hence the reason a massive main sequence star will not survive on the main sequence as long. It has a shorter life. Alright, it will die sooner. At the end of our main sequence, so going back to the small star, fusion will run out. Our hydrogen is only a certain amount. As soon as we finish burning our hydrogen, what happens at the start is our star will start to implode. Gravity will take over. There's no more proton-proton fusion, so the outward force is no longer balancing the gravity. The gravity will bring it in. But as a result of the gravity collapsing the star, it will actually make the pressure increase even more. So that compression will increase the pressure, will increase the temperature, which will raise from the 10,000 degrees Celsius that we needed for hydrogen fusion, and the temperature will hit the temperature required for helium fusion. So at the end of the main sequence for our sun, star starts to collapse, pressures increase again, temperatures go even higher, you switch on helium fusion. Now you're fusing helium, even more energy is created, okay? And if you create even more energy, in this situation here where before pressure and gravity were balanced, the pressure from the inside is much bigger than gravity. Helium will give you more energy and it will start to make the star swell. That's what happens when you become a red giant. So here, hydrogen runs out, helium starts to be fused, which is bigger, makes the star expand, becomes a red giant star. Like I said, that's going to make Mercury, Venus, and even Earth become engulfed by the star. Okay, so it'll be basically the end of the Earth as well, but it's a long way away. Now, it will get to a certain size, and we literally just discussed, as radius of an object gets bigger, the gravitational force pulling it back gets weaker, right? And the amount of matter that it's made of doesn't change, so it's still the same mass star. It's red because the bigger it gets, the cooler it's going to get on its edge, and the cooler the temperature, the lower the temperature, the longer the wavelength. So it will move back to the red part of the spectrum, longest wavelength, so it appears red. That's why it's a red giant star. And helium will run out. Now, our star is big, and a red giant is big, but it's not as big as some other stars. So even though it had high enough temperature to make helium fuse and expand to a red giant, When it reaches that red giant stage, it cannot go on any further. We don't create all the elements through the whole periodic table. We can only go so far. But because when we stop fusing, what we have in the core, the gravity is so weak that it is not strong enough to pull its outer shell back in. It cannot bring it back. So fusion stops, but it doesn't collapse at this point. It's so big that gravity is so weak, it cannot bring it back, so it just lets it go. The envelope of the star is so far away from its core, it doesn't bring it back in. It lets it go in literally a shell of gas, or what's known as a planetary nebula. And at the center of that planetary nebula, if you have a look at the textbook at the image, you've got a very nice kind of outer shell made of lots of different colors. And at the very center is a white dwarf. A white dwarf, there's no fusion, fusion's finished. It's just so hot that it burns very brightly, okay? No fusion is being burned, no fuel at all. It's just literally a very hot star which is very bright in the sky to us, okay? Back to the big star, exactly the same. Nebula, gravity collapses, brings it in. Pressures rise enough that temperature is hot enough, so wavelengths are short enough to emit visible light, but no fusion has begun. When it gets hot enough, it becomes a main sequence star because fusion of hydrogen begins. Outward pressure is balanced by gravity on the main sequence, even bigger, so it's burning through its fuel more, so it lives for a less time on the main sequence. Same again, hydrogen fusion stops, the gravity starts to collapse because there's no outward pressure. Gravity comes in, pressures go up again, temperatures go up again, so that it's high enough that helium can fuse. Helium starts to fuse, and again, remember, the pressure outwards from helium is even bigger than gravity. It goes bigger and bigger, and in this case, it's so big that it's a red supergiant. Now, this one has enough mass and enough energy that the helium fusion will finish, and then it can start to fuse more. It will start to fuse oxygen, it will fuse silicon. Every element that we have on the periodic table had to be created in the center of a star. So the fusion of heavier elements produce heavier elements and energy. Okay, so it literally gets bigger and bigger and bigger. We even have red hypergiants as well. They can go enormously big. Fusion will go only to iron. You can only fuse in the core of a star all the way to iron, which is the most stable element. You have a red supergiant where its core is made of pure iron. Even though the star itself is massive, and yes, gravitational field strength will go less as the radius of the red supergiant gets bigger, this time it is strong enough in the core that fusion has to stop. You cannot put iron and iron together. It has to stop. This time it's not going to let go of its envelope. The core is so strong because it's made of iron that it will collapse. It's strong enough that it will bring the star back in. The red supergiant will literally explode in the biggest, like we said, the biggest event in the universe, which is a supernova. Okay? At the end of the supernova, what's left again at the core is either a neutron star, which is a very, very fast spinning star made mainly of neutrons, very dense, very small, or it's a black hole. Something that we don't actually know the physical properties of, we don't know what it is, we just know it is one of the most massive things in the universe, but no light can escape, so we can't see it. Alright? They're your two life cycles, and that is literally everything that happens at every stage and why.